of gradient. So I calculate the variation. Yeah, I'm not referring it to anything. Now, what about, and then I can, okay, what about SSR? Is it actually this one? This is the one that I want to talk about. SS regression. Or maybe it's easier to understand SS residue. So R squared is defined to be SSR over SST, which you can show easily that it is 1 minus SS residue over SST. Now what is SS residue? SS residue measures the sum of square of deviation of each y value to the fitted line. So it measures SS residue, as I've explained earlier. The larger the SS residue, the worse is the fit, because you have points far from the fitted line. If all the points are very close to the fitted line, then your SS residue will be small. So you can think of SS residue as a measure of the variability in y remaining after x has been considered. So in other words, what is SSR? SSR is the variability in y after x has been considered. Yeah? So SST is just variation in y. But SSR is the variation in y after you have taken into consideration the regressor variable x. And SS residue is the remaining variability in y. So, so we know SSR is the variability in y after we have considered the regressor variable. So if SSR is close to SST, then R squared will be close to 1. Yeah? In other words, if SS residue is very small, so all the points are close to the regression line, and then your R squared will be large. However, if your points are far from the regression line, then your SS residue will be large, and then R squared will be closer to 0. So from here, we know that R squared can be used as a measure of how good the fitted line is, right? So if your R squared is closer to 1, that means the points are very close to the regression line. If R squared is, let's say, 0.3, then you know that the points fluctuates, pretty far away from the fitted line, so it's not so good. Whatever it is, you can show that R squared must be between 0 and 1, because SS residue has to be less than SST. So we now know a simple way to gauge whether a fitted line is good or not is to look at R squared. If R squared is close to 1, well, probably quite well fitted because the points are close to it. If it's small, close to 0 or 0.5, 0.6, then it is not. Another way to look at R squared is you can think of it as a proportion of variation in y explained by the regressor. So if R squared, let's say, is 0.7, then we interpret this as 30% of the variation in y can be explained by the regression line. Which means as x increases, y will increase. But it doesn't. All the points don't fall on the line, exactly. There's fluctuation. So 30% of the variation in y remain unexplained. That's what R squared is. So if you have R squared equal to 0.99, that means 99% of the variation in y can be explained by the regressor x. Because as x increases, y follows. And it follows very strictly. So you have a very large R squared. So for the rocket propellant data, you can calculate this R squared. And R squared of 0.9 is pretty good. It says 90% of the variation in y can be explained by x. And when you say summary of your fitted model, that's the model that you fitted, Ln. And R squared will be here. Yeah, that's called R squared. There's another one called adjusted R squared. We'll come to it later. Yeah, as far as simple linear regression is concerned, there's only one R squared. R squared, that's all. And don't worry about the term multiple, because this program is written for multiple linear regression. So R squared is the thing that we want. All right. Or you can use this to extract R squared, and then use it in your other statement. If you want this value, you can extract it. All right. So that is chapter 2C. So in chapter 2C, we learn a few things. We learn estimation of sigma squared, the mean response at x0, prediction of new observation at x0, mean of n new observation, and then the most important one here is R squared. I think these two are the more important ones. Sigma squared and R squared. So, I'm now ready to move on to 2D. So in 2D, we want to look at some consideration. So now, at least we understand, what is simple linear regression, but then there are some things you should be aware of, and that will be discussed under the topic some consideration in the use of regression, pages 3 to 10. After that, I will talk about a special simple linear regression model where the line must pass through the origin. You can find many applications of why the line must pass through the origin. Okay? Because when x is 0, y got to be 0. That's the reason why. And then we talk about maximum likelihood estimation as an alternative way of fitting linear regression. Again, if you have not heard of this word, maximum likelihood estimation, then I think, I don't know what to say. You are supposed to have learned maximum likelihood estimation. All right. So I cannot explain to you what, from the beginning to the end, what's maximum likelihood. If you do not know what it is, you really got to learn it now on your own. After that, we will look at the case when the regressor x is random. So far, I have only discussed one case, where the regressor x is a constant, what's the year of graduation? 0, 5, 10, 15. I fix it. It's a constant. It's not a random variable. What if x is also random, like the response? I give you a simple example. I take a sample of students from here. I measure the height. Height is I measure the weight. Okay, the weight. Weight is the regressor variable or the explanatory variable. I don't know which one I should use. No. Okay, x is the weight. And then y is the height of the student. So I'm trying to use the weight to predict what the height is. I mean, if you are heavy, quite likely you are taller. Not always true, right? That's why all the points don't fall exactly on a straight line. We have exceptions here and there. So this example is one where the weight and the height are both random variables. Because when I measure x and the height and weight from a person, both are random variables. I didn't fix the weight of a person in this experiment. So when x is random, how do we deal with this regression problem? We also want to fit the line and so on, And well, there are two cases. One is they are just jointly distributed. We don't know the distribution. The other one is they are normally distributed. No? XY binomial. Not binomial. Jointly normal. So something you learn in ST3131. Joint normal. I don't know whether I taught it or not. Last semester I taught probability. Well, but I did discuss joint distribution, right? So what if both are jointly normally distributed? How do we do regression? And so these are some special cases. So I would say this is a very special case. This one. Not so important as far as I think. Why is that so? Why is it that when x and y jointly distributed, this case is not so important? This is more important. Can you tell me a reason why the second case is not so important? X and Y are jointly distributed. That's given for almost all data sets. But for it to be jointly normally distributed, you really need a data set that exhibits that property. And not many data sets exhibit this condition. Jointly normal. It's a very harsh condition. So that's why this, unless you can prove that your x and y are jointly normal, otherwise you're not going to use whatever method that I'm going to describe here. Okay, that's what it is. All right, so let's look at some consideration in the use of regression. And consideration also means caution, for example. So I have 5 points here to discuss. Number 1, regression models are intended as interpolation equations over the range. So the key word here is interpolation. Yeah. This is the most common use for regression. All right, other than prediction. So what does that mean? So let me get to chapter 2a. I want a graph to show you. I just want a graph to tell you what interpolation means. So let's look at this example that I gave you earlier. Cholesterol level versus age. Age is your explanatory variable. Well, you can fit a straight line, but I still feel that, this a slight curve would be better. So interpolation means, if you tell me your age now, let's say you say 21, then I can, I can make a prediction that your cholesterol level is probably there. Now, this experiment is carried out, using subjects from 20 years old to, 62. For me, I'm not 62 anymore. I'm 67, going to be 68 soon. Very soon, I'll be 68. So, what is my predicted cholesterol level? See, I'm now beyond the range. If you predict my cholesterol level using this, then you are not doing interpolation, you are doing extrapolation. And that can be dangerous because is it going to continue? Or is it going to stabilize? Or will it come down, Or will it go up sharply? See, so when you do extrapolation, you can see there are so many possibilities. We don't know how this curve will behave beyond the experimental range. That's why whenever you do extrapolation, you need to be very careful. So let's go back to here. So that's interpolation, extrapolation. Number 2, the disposition of the x values plays an important part in the least squares fit. So what's disposition? Yeah. So I went to check the dictionary just to make sure I got it. Disposition means the placement or the position of the x value. Why would the position or the placement of the x value play an important role in the least square fit? Well, for that, I can explain to you using this result that we have. We can use this clean one. Okay, this is chapter 2b, page 3. So when we do least square regression, we can derive beta 1 hat and beta not hat. So this is beta 1. And it is a linear combination of the y, of the response. Which means you are using the weight Ci for the observation Yi. So every observation is given a different weight for estimating the slope. Can you see that? Unlike unlike y bar, which I've explained to you, every observation is given the same weight 1 over n in estimating sample mean. But to estimate the slope, every observation is given a different weight. According to what? According to the disposition of the point from the mean. So if you are, let's say if xi is near x bar, then Ci is what? 0. or near 0. It means you have very little weight in your scale, you know, what beta 1 should be. But if you are far from sample mean, then hey, you have a big say. You will have a big influence on beta 1 head. So that's what it is. If you want to explain it in a theoretical manner. Okay. Well, so that's what it is. Then what about outliers? Okay, let's take a look. So these 2 points, suppose you don't have these 2 points, the fitted line will be this. Yeah? If you have these 2 points, if they are there, then it will be this. The fitted line will change drastically because A and B, because of the disposition of A and B, they are far from the mean. X bar is somewhere there. They are far, and they exert big influence on the slope. Okay. This point also. This point is also exert a strong influence. Without this, maybe the line will pass through here. With this point, it will pass through here. You know, it can cause a drastic change. And what is outlier? Outlier are defined to be observations that differ constantly from the rest of the data. So now I'm just going to define outlier in a very casual manner. Any point that is far from the majority is called an outlier. Okay? So if I give you an example, if most students get score between 40 to 60, and if you score 95, okay, then you are an outlier. If you score 2 marks, hey, you are also an outlier. So outlier doesn't mean something good or bad. It could be good, it could be bad, depending on the situation. But outlier simply means a point that is far from the majority. So if you want to form a basketball team, you want outliers, right? You look for people who are extra tall. You don't look for normal people. This is normal. If you can find someone who is 8-footer, hey, you win every game. Just stand there. You can block every shot. Okay? All right. Now, the next point actually is easy to understand. But sometimes, you perform an analysis of data. You find that, R squared is very, very large, close to 1, like 0.99. Then you are very tempted to say that y depends on x. Y and x has a close relationship, very strong relationship. X causes y. Well, what does the statement here say? It says, strong relationship between 2 variables does not imply that the variables are related in any causal sense. Causal means causes. Like if you smoke, it causes cancer. Because they've done experiments. They let a group of rats to smoke every day, Another group of rats, no smoke at all, clean environment. And then they found that these rats that went through this smoking, all day in a smokehouse, they developed lung cancer. much easier than the other group. For example, you work in a casino. You know, in Singapore, all indoor places, you must not smoke. If you are caught, you get fined $1,000 or something. But there's one indoor place you can smoke. Where? Casino. Because I think the idea is, if you don't care about your life, why care about smoking? You go there and gamble your fortune away, you don't care already. So you can smoke to death also inside there. Either you gamble to death or you smoke to death. They don't care. So, smoking causes lung cancer. It's proven. So how? Of course, some people say, hey, you know, I've seen this old man smoking all this stuff, chain smoker at the HDB void deck. Every day I go to school, I see him, 90-year-old still smoking. Well, good luck to him. You know, some people have some immunity to smoke or something. So it's an outlier. But when we talk about research, we don't talk about these outliers. We talk about the general trend. How would the general population react to it? Yeah. You know, I have also seen some very silly messages. You know, they say, you know, the guy who invented this bicycle for exercise, you know, died very young. And the guy who promote sensible eating habit also died very young. So the conclusion is, forget about all this, just do what you want. All these are so illogical, you know. So what's the point here? So when you perform regression analysis, you find that R squared is 0.99. You're very tempted to say, hey, X causes Y. If I change X, then Y must follow. It causes it. But this is not true. So here I have two examples. Yeah, one is mental defectives. This one variable. The other one is the radio licenses. This is a pretty old data set, but I think it explains this idea very well. So number of defectives means what? Number of certified mental defectives per 10,000 population in UK. So that's a response. So 8 means 80,000, okay? So there are a lot of crazy people walking around in UK. In 1937, 23,000. 23 times 10,000. Now even more, maybe in the millions. That's why there's riot, you know. I don't know. Okay. Mentally defective or not. Okay, so here we have a data. Why? And then someone look at the radio licenses. How many radio licenses that they issue up? So it also increases. I guess it's not difficult to understand why the number of mental defectives increases as time goes on, right? Do you know why? You should know why, unless you are also mental defective. What's the reason why it should go up? The number of mental defectives. Very scary term, huh? Because the population increases. You know, a fraction of the population has to be mentally defective for some reason or other, due to stress from taking ST3131 or whatever, you know. There are many reasons, or from family, from lover, from this and that. So the number of mental defectives keep going up because population goes up. And then the number of radio licenses also go up. As time goes on, more people apply. So what if you fit a regression line for these two? You fit it, see what happens. So I have Y radio license, mental defectives. Here's the radio license, X1. So I fit a model. And then it says there's a p-value is very strong. And look at this R squared. It says 98% of the variation in the number of mental defectives can be explained by the number of radio licenses. So does that mean you issue more radio licenses, you are going to create more crazy people around? Then stop issuing, stop, make it zero. And then all the mental defectives will disappear suddenly. Will it happen? No. That's called causation. It doesn't cause it. It just happens to be correlated. The next one, you will surely understand why. High R squared doesn't mean your model is useful. Do you understand? So here's the first name president of United States. Calvin, number of letters, 6, 7, 8. So this is X2. So what if we try and look at mental defective versus X2? See whether R squared is high. So this is X1. See, linear relationship. This one also very high. So don't try to choose a president with a long last name. You get no crazy people around. Huh? I think Trump is fine. Trump is 1, 2, 3, 4, 5. 5 is okay. Not too bad. So the story is you don't, even though R squared is large, close to 1, strong relationship does not imply causation. Causation does imply strong relationship. Okay? Alright. So next is we are going to look at a very special case of simple linear regression, which is one where there is no beta known. So actually here, when I write the model this way, I'm forcing the line to pass through the origin. And I can form the least square equation. There's only one unknown. I differentiate it and set it to 0. I can find beta 1, and it looks like this. And then you can show that it's unbiased and so on. And also you can estimate this. So this all can be done very similar to the the more general simple linear regression model that I've discussed. And my tutorial is focused on the general case. So if you want to know the derivation of all this, you can actually go through it on your own. So you can also calculate 100% this confidence interval for beta 1, and then for mean response. You can go through very similar derivation or prediction of the future observation. Alright? And then here's one data set where, this is about delivery. Self-stocking data. You have how many cases that you want to stock, and that's the time taken. So the more cases, the more time you need. So time required for a merchandiser to stock a grocery store with a soft drink product. Cases is the number of cases stocked. So you bring all these cases of soft drink to the shop and you stock it up for them. If you have more, the time will be longer. If you have less, you take less time. So if you have 0 cases, then you should spend 0 time, right? That's why it has to pass through the origin, this one case. If you don't set beta naught equals 0, you might get a line with beta naught that is non-zero. So you can calculate all this I just want to point out one thing. In fitting a model without the beta naught, all you have to do is say this. Just say tilde 0 plus case. Then it will force beta naught to be 0. Okay? So that's one thing. That's the only thing that I want to highlight. So here you can, force the line to pass through the origin, as you can see. So as the number of cases go up, time will also go up. And then you can do tests of hypotheses, calculate R squared. R squared in this case is really very strong. 99.8% of the variation in Y can be explained by the line. And beta 1 definitely, it's very, very strong evidence that beta 1 is different from 0, as you can see from the graph. So it passes through. Yeah, very strong relationship. All right, maybe you take a break now. So, so in the first half of the lecture, I talked about R squared, which is very important. It is the proportion of variation in Y explained by the regressor or the fitted line. And then we look at some consideration on the use of regression. And then I talk about a special type of simple linear regression that must pass through the origin. Okay, so let's take 5 minutes break, and then we can continue. For simple linear regression, our approach is to minimize the sum of square of error. Well, you could also minimize the absolute error. These are two different approaches. But I'm not sure whether you get the same answer. Quite likely they are different. Now here, so this is the method 1, method 2. This is not easy. This is method 2. So I'm not showing you method 2. I think it's not easy. Method 3 is easy. And method 3 is a very powerful method that uses statistics. This method is called maximum likelihood estimation. Basically, you have Y, the response, you know that it's normal. We are still using the same assumption that epsilon follows normal distribution. So the response follows a normal distribution. And you form a likelihood function, maximize it to get all your parameters into. So we'll look at that to see how we have, look at this alternative approach. I think in probability, I have also, last semester I taught probability. I've also talked about this maximum likelihood estimation procedure, where, I believe I apply to estimate the number of animals in a forest, if you can remember. Yeah? So, here, let's go through the basic assumption one more time. You have the data set. It follows this model. The epsilon is assumed to be a random variable with mean 0, variance independent of I, and they are also independent That means the two observations are not related in any way, any two of them. And assume they are normally distributed. Because of this, the y, they are now independently and normally distributed. Because of this assumption, we got this. And so, what we have is this. So with all this assumption, we now know that yi, they are independent, normally distributed, with this mean and the variance, and this as the variance. So we know the mean, we know the variance, we know the distribution, so we can write down the density of yi. Now if you look at this density, how many unknown parameters are there? 1, 2, 3. Pi is not an unknown, pi is a constant. So there are 3 unknowns. And we want to estimate this using the maximum likelihood approach. So the first step is you form the likelihood function. Likelihood function is just a product of all the density of all the responses. So you just take the product. So this big pi, capital Pi means the product. You take the product of these n normal densities, simplify it. Yeah, simplify it. And then take log. Take log. Okay? Why take log? Because actually at this step, you can already try to maximize it with respect to beta naught, beta 1, and sigma squared. But usually, for maximum likelihood approach, it is easier from experience, okay, that if you convert it to log, if you look at log of L, log of the likelihood function, you can do differentiation much easier. It's simpler. And when you minimize logarithm of L, it is the same as minimizing the likelihood function L. There's no difference. The answer you get will be the same. But then logarithm of L is easier to differentiate. That's why we use log of L. So take log of L, you will get this. And then you can now differentiate this function, this log of L, with respect to beta naught, beta 1, and sigma squared. Remember, this is a partial derivative. That means when you differentiate with respect to beta naught, sigma squared and beta 1 are considered constant, and so on. Okay? And then set it equal to 0. You will be able to find maximum likelihood estimates of beta naught, beta 1, and sigma. So here's the answer. Right here. If you look at beta tilde, so this estimate from MLE, we use a different head. The other one is a head. This one is a tilde. So beta tilde is the same. Exactly the same as what you get from the least square approach. Beta naught tilde is also the same. So what's the difference? The difference is here. The other one, for least square approach, is n minus 2. If you use a maximum likelihood approach, you get n. So there's a slight difference. For small sample, it matters. For large sample, both of them are practically the same. Okay? So this is this is the one based on least square approach. So you can see that they are the same. As the least square except for sigma square. So now we know how to estimate beta naught and beta 1 using two different approaches. One is minimizing sum of square errors. The other one is maximum likelihood estimation. Okay? At least we know two methods. Now what about, now let's consider the case where the regressor X is random. What do we do? You know, I show you the other example, right? You collect a sample, measure the weight and the height. Those are random. Or I interview household, you know. Let's say number of children as regressor, number of people in the household versus the household income. That's another way. And this case, where X is random, is very common in linear regression. Many problems, whenever you do an observational study, you will get random X. If you do an experiment, you know, then you can fix X. I fix year of graduation to be 5, 10, 15. Or I can fix, I only want, you know, 5 people whose weight is 60 kg, yeah, or 70 kg. I can fix it. Then it becomes non-random. But random is common because we do observational study. So what happens is, if X is random, well, how are we going to do least square regression? Because so far, up to this point in time, our definition, our assumption, is all based on what? Let's go back, take a look. It's all based on, these are our assumptions. Here. The assumptions are here. Right here. The model and the assumption. There's only one random variable. X is a constant. It's fixed. It's non-random. Yeah? It's not a constant, but it's non-random. So what if, so based on this, you know, we minimize it to get beta naught, head, beta 1 head, and then I also went through, you know, confidence interval, hypothesis testing, and all this. Some of this, of course, I ask you to do in tutorials. So all these are all done up now. If you want to make a prediction, yes, you can use this formula and so on. But what if, but all these are based on X non-random. What if I do an observational study and X is random? Will all these results still hold or not? If they don't hold, then we are in trouble. We have to prove all, you know, derive everything again by considering X to be random. Okay? So, well, fortunately, good news. What's the good news? The good news is it can be shown that all our previous results hold if these two conditions are true. All right. Number one, the conditional distribution of y given x is normal with conditional mean this and that. So this is an easy condition because given x, y is you can probably show from many cases that is also normal with this. If this condition is not true, then we are in trouble. Okay, then you cannot use whatever result that we have derived. Two, the X are independent random variables whose probability distribution does not involve this. So you have to make sure these two conditions are fulfilled, and then you can go on and use whatever result that we have. So now, so what happened now is, in fact, in applications, people now, they just use it. Whether X is random or non-random, people just use it. They always, but I want you to be careful. When X is non-random, you really have to try to justify these two conditions in some way. Maybe not so easy, but at least you have to think. Given X, is Y going to be approximately normal? At least you can check. You can do some check. Yeah? Or will X has distribution that does not involve this? Maybe this one could be true for many data sets. So at least you need to check. So the next one that I want to consider is a very special model where X is non-random, not only non-random, but they are jointly normal. They are jointly normal. And this is called a correlation model. So, as I've said, this case is not so important because it is not so easy to find a data set that is jointly normal in practice. Or at least I've not used it in my entire career, trying to do something like that. But I think it's interesting enough for us to take a look at this model. So what happened now is, you have two random variables, X and Y. They have a joint normal distribution. And they are, so this is called a bivariate normal distribution. I think probability I only talk about joint distribution. I did not mention this bivariate normal. But it's just a special joint distribution. There are 5 parameters that determine this distribution. The variance of X and Y, the standard deviation, the mean of X, mean of Y, and then there is this one called the correlation. So X has its mean and variance, Y has its mean and variance, and then you have another parameter called correlation. So the correlation is the correlation between X and Y. So I have a picture that shows you two bivariate normal distribution. One of them, you can see, if you look at it, it's like a little hill, small round hill, and if you cut across, you can actually see circle. And this has correlation near 0. But the other case, it is compressed in some way. Because there is correlation, there's a strong correlation. That's why this joint density is in a compressed form. It shows, if X changes, if X2 changes, X2 changes, X1 will follow very closely. So this is a bivariate normal, and you can. Okay, do I need this? I think I got this. Let me just take a look. Give me a minute. use the maximum likelihood approach to find beta naught and beta 1 for this particular problem. And then you can also find the conditional distribution of y for given x value. Okay, so what happened now is, so these are actually all the properties of a bivariate normal. You can eventually show, in probability, I show you how to extract the distribution of one of them, right, from the joint. So you can go through this, and you can find the conditional distribution of y given x. And you can show that it is actually normal. So, so this is not something new. So if you have taken probability, you should be able to derive this result quite easily, that y given x is normal with this as the mean and variance sigma 1 2 squared. But what we are really interested in is this one, the correlation. The correlation defines the relationship between x and y. It's like the quantity beta, the slope, which determines the linear relationship. So for such a case here where you have a bivariate normal, we want to test this. We want to test whether this rho, this RHO, is a Greek character, whether this correlation is 0 or not. If it's 0, then there is no relationship between x and y. But if it is not 0, then there is a relationship. And that is the population correlation. But we can use the data to calculate the sample correlation coefficient, which is something you learn in ST3131, the introductory statistics course. So R is the sample correlation coefficient. And with some manipulation, you can show that this sample correlation is related to the slope when you fit a line through. It's actually a function, linear function of R, this one. So if R is large, this tends to be large. Another more important relationship is this. This sample correlation coefficient is exactly the same as R squared. The proof is that it's very simple. Yeah, you can go through that. So, but remember, this sample correlation coefficient has no meaning if x is non-random. It's only meaningful if x and y are both random quantities. So, as I've said, if you want to test whether there's any relationship or not between x and y, we will either test beta 1 equal to 0 or not, or we can test this. You can test whether the population correlation is equal to 0 or not. Okay? So for this particular case, where we have a bivariate normal, instead of testing beta 1, we can test the population correlation coefficient. And there is a statistics that we can use for this purpose. I'm not going into the detail on how this thing is derived, okay? But I guess if you're interested, you can always Google search for the article and read up how people found these statistics. But you can, if you read the article, you will know that this statistics has a t distribution with n minus 2 degrees of freedom under the null hypothesis. and then you can reject the null hypothesis if the t statistics is too large. So if r is near 0, then t naught will be small. Then you will not reject the null hypothesis. Now, so, in hypothesis testing, sometimes we also want to test whether the slope is 2 or not, instead of 0. Here we can also do that. We can consider the case where, here, you can consider this case, where rho 0 is not necessarily 0. Now, for this case, you will need another test, not the same test. I'm not too worried about the origin of this test. If you are interested, you can always Google, search for the article and read. Some statistician found that discovered this test, put it this way. And the test statistics, or at least the research, show that if you have a large sample, this z, which is the, what you call the inverse of the hyperbolic tangent, r, is approximately normally distributed. By the way, this is inverse of the hyperbolic tangent. And it is defined to be this. So if you are intimidated by this arctangent r, don't be so. Because you can actually, it is actually just a definition in terms of this. Half times log 1 plus r over 1 minus r. So if you want to feel better, not to be intimidated by all this, you can just consider z to be half times log 1 plus r over 1 minus r. Okay? Now, so these statistics it can be shown to be approximately normal with this mean and this variant. And so if you standardize the test statistics, you can standardize it, and then you can use it to do, so this will be standard normal, and then you can use it to do tests or construct confidence interval. Yeah? Remember, inverse of the hyperbolic tangent is here. So here's the definition. Let me just grab this now. This is the definition, okay? For one more stroke. Okay, I'm just going to demonstrate this case where we have bivariate normal with an example where we are going to test correlation coefficient equal to 0. So here I have the delivery time data. I have case and time listed. Yeah, the case and the time. So if I have less case to deliver, the time will be shorter, and so on. And I want to test this. I want to test this one. So I will use, so there are two separate tests here. One for this equal to 0 and the other one for non-zero case. So you can calculate R and then check it out whether you should reject it or not. So in R, you can use this function here to calculate the correlation, and after that you can calculate the test statistics and then the p-value, and or you can use this to calculate the confidence interval for this case. Okay? So correlation. So if you go through it, you can find P naught, p-value, which is very small, nearly zero. So there's strong confidence, strong evidence that X and Y are related. Okay? And then here's a confidence interval for the correlation coefficient, which is very high. And p-value is very small. You reject a null hypothesis. Finally, I just have a small appendix here to show you some of the functions that you can use to extract certain values. Okay, so you might find some of this useful in your ARM programming. All right. So I guess I'm done. So let me just summarize what I just said today. So in the second half of the lecture, we look at maximum likelihood estimation as an alternative approach to least square regression. And in observational study, X can be random. And if two conditions are satisfied, all the results that we know will still apply. And if they are jointly normally distributed, then we have a different approach altogether. We will be studying using correlation coefficient. Alright, so we prepare for the quiz next week, Monday and Monday. So we have during lecture, either during the lecture or after, or at the end of the lecture.
You only change one parameter, but you change. They tell you to only change.
Is it only can edit tasks?
Yeah, this is the one. This is the one they give us, right? I think. Wait, which one did they give us?
It's correct though.
No.